So hello, today I'm going to present this paper. It's called Interactive Motion Mapping for Real-Time Character Control. It was presented in Eurographics, this last Eurographics, and it comes from the Max Planck Institute. So the goal is actually nowadays, like the tense in computer games and activities, is to actually provide some interaction. So actually, for example, like the Kinect, these kind of things, nowadays is based on not just the game controller, but the human body. So the goal of this paper is actually to provide some intuitive and kind of real-time character control for these kind of situations. This can also be used for prototyping in animation. So if you can actually perform in front of the computer and then just set up some easy animation by yourself, then you don't have to actually control the character very key. So, well, nowadays in real-time character control in video games, usually like the character is controlled by using a game controller. Now, also you can start controlling the characters by using some kind of motion retargeting. So basically, transferring your motions from one skeleton to another skeleton. So in recent works, what happens if actually the motion is the skeleton's configuration is very different. So there is no even mapping between these two. So there is many related works. It's been an interesting topic. So actually, some of the most recent papers is actually one from our previous PhD student, which was done in SNU. So actually, in this case, they learned some mapping between some motions between the skeletons and actually some different configurations of the very different characters. So as you can see here, depending on actually the hand's position and the motions, the characters do different things. So for example, like the hands in this case controls the front legs, and actually the lower legs somehow control the rest of the body. So, but it's still based on skeletons. So it's some kind of in between motion retargeting and mapping and learning some behaviors. So another approach is actually to somehow consider everything as a human. So basically, you have the idea in this case is something, if you see the movie from Pixar, like the Flexo, it's like you can consider almost every object is like a human. So in this case, it's mapping the human skeleton and provide some deformation to create some kind of human-like behavior on very different objects. So basically in these existing approaches, there is some skeleton-based body control, but actually it takes a lot of time to define good mappings, and it's not easily to define these mappings. How can you actually control, in this case, well, there is 4 legs. How you define this, it's not clear. So this is one of the problems. So in this case, it opens more challenges. For example, like what happens is actually there is no skeleton. Some motions cannot be actually, or some characters cannot be actually well defined by some skeleton. For example, like the caterpillar has some kind of non-linear deformation, which is actually a little bit difficult to represent with a skeleton. And also what happens if actually the input is not just a skeleton, what happens is actually it's a face control. Can we control this character by using face motions or anything, or your hands or anything? So another problem would be what happens is actually the user is not really good at performing the mappings. So actually if you map, the mapping problem usually is like if you map like the circular motion, then if you start doing up and down, then it's not well defined. So the result will create some kind of strange motions if actually it's not performed in the correct way. So finally, another challenge is actually how to define actually these controls in an easy way. So what would be the motions that best can represent some mappings? For example, like if you decide to do up and down for one mapping, and then actually you do down and up. Maybe it's very similar motion, so maybe it's better to just do like a horizontal motion. So usually the users are not aware of these things. So actually the goal is to provide some kind of easy visualization of whether your mapping is good or not. So basically this is actually the results of their method. So basically here you have a character controlled by a person. So the walking motion here provides a walking, and then the hand somehow provides some kind of jumping around. You can see that actually he can control the rotation and the translation, the motion. So and these are actually controlled by the velocity or this thing. So it provides kind of good control of the whole character. So how is it done? In overview, basically we have some kind of user motions. We have some kind of tracking device which actually captures some kind of features, which we call the input motion. Finally, we have some kind of motion mapping into some other character motion. So more technically, like the user motion could be anything. Could be full body, facial expressions or articulations of the hand. Then actually their definition is here, we don't need a skeleton. We can just actually consider this as a point cloud. And finally, the character motion, they consider it just a mesh, no skeleton, no rig. So in this case, first they have an example. To learn the mapping, you need some examples. So the first examples is actually some set of actually animations that will be used to actually, that represents the character's possible motions. So in this case, we have a sheep which is walking and then jumping. So actually this example animation is based on key poses. Then we have a motion mapping. So basically using some correspondences, usually in the paper they say they just need 5 or 8. Then in this case, they can find some correspondence between some pose and some motion. Finally, once this motion mapping is learned, they can actually, for any new pose of the person controlling the character, then they can generate some new motion. So actually, how this works. First, they have to define a correspondence between both characters. So actually the goal in this case is actually to do it in an easy and flexible way. So the idea is actually that this mapping is not just chosen somehow carefully. It has to be done in a kind of real-time interactively. So that's why it's called performance-based. So as you are learning, as you are performing in front of the capturing device, you can see how the mapping is evolving. So actually they provide a measure on how actually the mapping is good or not. So if you see that you are doing something that the system considers that it's not good enough, you will have some visual feedback and then you can change the mapping on real time. So another approach is actually, usually when you define a mapping, you need many mappings, many example poses. So actually they try to achieve a good mapping with as few poses possible. And actually the guided is actually, the system somehow guides you in whether, sometimes it suggests what would be, if you already choose some few correspondence, he would actually suggest what kind of new poses can you use for a better mapping. So all of this is because usually the normal user is not aware of how expressive a motion is. So basically, if you are a scientist, maybe you know the concept of variance or kind of similar poses, but actually the user doesn't know. So the idea is actually the system will somehow guide you in whether the mapping is good or not. So here's an example of how the mapping is working. So as you can see, in the first you have to find a correspondence for like the first motion. So in this case, now he's doing very similar pose. So the confidence score is very low. So this way, actually, you can see how actually your mapping is going. So the basic idea is actually, if you are repeating something that you already did before, then actually the motion will be kind of bad. So after this, for this very similar, for just these 8 correspondence, they can actually generate this mapping, which can control the character with this system. So actually here is how do you actually map the character. So actually once you have the correspondence, actually you need to learn some mapping from one input pose, which is not actually the ones from the correspondence, to actually generate a new character pose. So this is actually learned by doing a linear mapping. So basically for your correspondence, you have a correspondence and then actually one character pose. Actually here in this case T1 means actually the velocities from the previous motion. Basically, actually the representation is a bit complex. Here it looks like it's just the previous pose, where it actually the velocities from the previous. So for example, like if you have a pose like this, but the previous motion was down, it's different from actually having the first pose up, because actually the motion is going down or going up. So actually considering the velocities in this second part helps actually separating similar poses. So this mapping is actually learned by Bayesian regression. So actually the advantage of the Bayesian regression is that it has an explicit noise model. So you can incorporate some kind of noise model, in this case Gaussian. So it can somehow eliminate some of the noise that might be in the input motion. And actually it provides a good estimate of what would be the most probable character pose according to some input. Also, it provides a good estimate of the variance of the prediction. So it means it's actually, if the prediction has a very small variance, it means actually the prediction is good. However, if the variance is very large, it means that it's actually very close to some existing input motions. So in this case, they use this variance to provide some confidence bar whether the new mapping is good or not. So now the second problem is actually they use very sparse set of correspondence. So this means that actually the new inputs are not well considered, so it could be a little bit everything. So they have to somehow reduce the range of motion of the input motions. So if there is no consideration of the range of motion, you can see that actually the character can suffer very strange deformations. Even for actually, you can see the learning before was very simple, just like circular motion and walking, but it is doing very different things. So we have to somehow discard these strange motions to keep it inside the range of motion of the target character. So to do that, actually they use, the goal is to exploit the other keyframes that were not used for actually the correspondence and learning the mapping. So out of these examples, we can actually extract something like the range of motion. So actually the goal is actually generate what they call a latent volume. So basically they have a representation of the mesh. So actually they put all these meshes into one very high dimensional space, which is actually like a pose space. Then in this case, the goal is actually somehow find the bounding volume that somehow represents all the possible poses that this character can achieve. So this is done by actually finding just do a simple PCA analysis, and then actually in this case you can also reduce the dimensionality. So as in the paper they mentioned that they just remove all the dimensions up to the 99% variance is contained, and then for each of the PCA axis, then you can find actually the bounding values. So in this case, although it's not perfect, most of the poses that are not in the character can be somehow discarded. So actually applying this method, so you can see for the same motion that we showed before, like if there is no this kind of prior information on the range of motion, the character will suffer very strange deformations. However, by using this, actually the character motions are somehow restricted inside the possible motions. So actually the result is not very good either, because actually he's doing not the motions that he specified for the mapping. So still produce some error in terms of actually the motion is not natural, but in terms of character deformation, it's still somehow poses that are related to the existing poses. So now, actually, in this case, we just consider the pose. But actually, usually when you're puppeting, what you want to do is actually move the character somehow. So from the existing animation, we can learn actually somehow how the pose is actually affecting the global transformation. So in this case, for each pose and the previous pose, we learn actually a global motion. This global motion means a translation and a rotation out of this thing. So now actually for how the shape is represented. So previously we said that actually the target mesh is represented as a mesh. But actually if we just use a very simple mesh representation, which is like vertex positions and connectivity, this will actually produce some errors. You can see that actually like the mesh is somehow interpolated, so actually the legs has some kind of motion, some kind of artifacts in how it grows. So actually a better representation is actually to consider how actually the mesh deforms between keyframes. So in this case, the solution is to represent the mesh as a set of vertex plus some phase rotation and shear. So actually, this actually encodes how actually each triangle is rotating between frames. It's a very similar representation from the deformation gradients paper, which is kind of famous in this field. So as I said, this model somehow encodes the rotation of each keyframe. So actually the reconstruction actually is quite fast, so actually you can still do it in real time. So in this case, from this mapping, you can see that the synthesized motion actually is more natural. Finally, for each sequence of the target mesh, you actually get some mapping. So now in order to combine all of them, basically you just mix them together by actually adding both motions. And finally, like the intensity can be actually adjusted by some, this has a property that actually if you actually walk slower or faster, actually the motions will be actually transferred faster. So because they encode actually the velocity, then actually this can be used actually as a means for more expressive puppeteering. So here are some results. For example, here is a mapping for the ship. So actually the jumping is encoded by actually jumping. So here's an example actually using the face. It's actually since actually the face is not the best how to say, the best input motion for anything, because actually the face is highly correlated. Actually all the faces look quite similar. So in this case, when using the face, they can actually produce very limited amount of motions. But they can also use actually the leap motion. In this case, actually the input motion is just 2 points in the 3D space. So some of the points is actually the human coordination is kind of limited. So actually the degrees of freedom is not that high in terms of actually what can you achieve. And finally, the granularity. So actually, usually the mapping for kind of real-time applications is very important. So if you can actually do a mapping just between very fast, then actually users will like it more. There are some examples like the face shift. I don't know if you know, it's a Kinect facial tracker. So actually, you need to spend actually almost 2 hours setting up your mapping. So it means you have to reconstruct your face. Then for each expressions that you want to map, you have to actually do a facial reconstruction. So basically, the mapping takes a lot of time. So actually, this is useful for some kind of movie that actually you want really high quality. But actually, for kind of games, if you have to spend 2 hours to actually set your mapping, then actually the user might just go play something else. So finally, a summary of the contributions here is actually they apply this to anything. They don't need to be skeletal animations. So actually, the solution is to actually provide a new character representation in terms of shape space, which encodes velocity. Then to deal with the noise, they provide the latent volume. And finally, they provide a guided corresponding measure and very few sparse correspondence to actually provide an easy definition of the mapping. So they achieve actually kind of robust character which is not depending on the skeleton. So it means that it can be applied for, actually their examples is only based on existing animations, but it could be also applied for simulations, like controlling water simulations, like waves or splashes. As long as it's just a mesh with some key frames, then they can achieve any kind of mapping. So the interface is also easy to learn for anybody. And finally, as long as you can actually get some feedback on actually how the mapping is doing. So you can change it anytime in very fast. So yeah, so here are more examples. So in this case, so because it's just based on point clouds, some existing animation can just provide, I mean, they don't need to be a human person. If you already have some animation, then you can just transfer it by using this. So yeah, that concludes my presentation. So if you have any questions. Okay. Then thank you for listening. Yeah. Uh, faster is not really. Yes. Well, the main benefit is actually you can actually map anything as long as it moves. So for example, like as I mentioned, if you have a simulation of a water, actually like a water splashing or some kind of water moving, you could also mapping this to anything. It's just a sequence. It could be also kind of images, like anything. As long as it somehow moves in terms of mesh positions, then actually you are not limited to actually join. So the most clear example would be like simulations. So you could control like a building just collapsing. You could have a simulation of actually a ball actually smashing into the building and then the building somehow collapsing. It could be very complex in terms of geometry, but actually you could somehow still mapping the collapse of the building to just your hand motion. So these kind of things cannot be with the skeleton. I mean, this kind of, or the skeleton configuration would be too complex to actually provide this. So for characters, in this case, well, it's not, you depend on your rig, right? So, but if you have a rig, then actually you still have to define some motions. So it's a kind of, the main contribution is a generalization of, it's actually going to the, let's say like the previous work by Yongo, it actually works quite well, or similar results, but it's just limited to characters, right? So the goal is actually provide a generalization of that approach, so that could be applied to anything. So in terms of practical situation, I mean, to generate the input motions, so in this case, to generate this kind of input motions, probably you need a rig. So in this case, since this is a character, then probably you can still use the previous method and it will work quite fine. But it's more like a intellectual exercise to just generalize in terms of mathematics. So let's say like the join in this case is just a particular case from the framework. So, yeah. Any other question? Okay. Thank you.